Hello and welcome to Introduction to Astronomy, AST 1002. It is my great pleasure this semester to be your instructor/professor. My name is Michael Jaramillo, and I will be guiding you through this course and hopefully inspiring a lifelong love and passion for astronomy. So before we get into all of the nitty-gritty of astronomy, let's go over what we're going to learn together this semester. So in this course, we will cover what is astronomy, what is the science of astronomy, and how do astronomers define the universe. We will d- learn together what humanity's place in the universe is and where we are in the universe. We'll also go over what physical units are used in astronomy, because a lot of the units that we use in our everyday are not very applicable to astronomy. We'll also go over the philosophy of science, so you will be able to know what ideas are scientific. You will understand the scientific method, how it's applied to astronomy, and you will then also be able to determine what is pseudoscience. So you will know very well that astrology is a pseudoscience and astronomy is a science. We'll also learn what scientific tools are used to study the universe. This is everything from a telescope to a particle accelerator. There are a lot of tools used in astronomy and those a lot of tools that are used to study our universe, and we'll learn about them in this course. So, what is astronomy? The OpenStax textbook very rigorously defines astronomy as the study of the objects that lie beyond and include our planet Earth, and the processes by which these objects interact with one another. This is a little rigid and wordy, and it also doesn't quite paint the big picture. So, in a little more simplified and a broader definition for this would be astronomy is the study of the universe. Now you may ask, well, what is the universe? Well, the universe is the totality of all space, time, matter, and energy. Now that is a little wordy, and you may be wondering, well, what exactly is space? What exactly is time? What is matter? And what is energy? What do those mean scientifically, and how do we define them? So let's explore this definition together. We're going to know very well what these terms mean by the end of this lecture and by the end of this course. So we'll start off with matter. Matter refers to the physical stuff or substances or particles which occupy space and possess a mass and have energy. Now, this may sound a little complex, because it's now referring to things that we are still trying to define, because right now, we still haven't defined what is space and what is energy, but we will get to those. So matter is everything that we can see and we can touch is a part of what we refer to as the visible universe. All this matter that we call visible matter is emitting and reflecting and absorbing light in wavelengths that we can see with our eyes. Now, our eyes see only a small fraction of what we refer to as the electromagnetic spectrum. In this figure that we have on this slide, we can see the full electromagnetic spectrum in its various wavelengths, starting with the radio, which has pretty long wavelengths on the size of meters. And then we have microwaves, which have smaller wavelengths. And then we have infrared, which is what we think of as heat. And if you've ever looked in night vision goggles, or you've seen a science documentary where they show what a snake can see, that is looking in the infrared. And then there's the visible light. This refers to the part of the spectrum that has everything we can see. All of the light in the rainbow is a part of the visible spectrum. Now, outside of the visible spectrum is where we start to get to higher energy wavelengths. This is like the UV that we have coming from our sun that we have to wear sunblock for. Also, some sunglasses have UV filters in them. And then we have X-rays. If you've ever broken a bone, you've had it X-rayed, very likely, and that it shines a light that is a wavelength that we can't see through your broken bone area, and the light goes through your skin, but is a kind of absorbed a little bit by your bone. It's your bone stands out in the X-ray. And then finally we have gamma rays, which are the highest energy form of light and are often produced in things like nuclear reactions or in some very energetic events like supernova in space. And so the wavelengths outside of the visible part of the spectrum are what we refer to as the invisible universe. Next, we'll talk about energy. Energy is the quantifiable capacity for matter to generate motion or move in space with respect to time. So if matter is able to do something rather than just sit there, like if it is moving or it is got some, it's in a system with gravitational energy, it has some kind of energy to it, which will allow it to move. It will allow the system to change. And energy is what we refer to this quantity of being able to move or change in time. So we've all heard of Einstein's famous equation, E equals mc squared. We see a little bit more complex version before us, which states that energy squared is equal to, in parentheses, mc squared, that whole thing squared, plus this last term, pc squared. And so we have labeled each one of these that the total energy of a system is equal to the mass energy plus the kinetic energy. I know this is very complex, seems very complex, and you don't need to know the exact mathematics of this because we live in a world where we are moving relatively slow compared to light. So our kinetic energy term can be thought of as very low or almost zero. Unless something is moving close to the speed of light, this last term, pc squared, is not very important. And so it can be thought of as zero if something is moving slow. I know that I will never be traveling near the speed of light, hopefully. So my kinetic energy term will always be small compared to my mass energy term. And so mass energy is it's like the innate energy of matter. All matter has an internal energy because matter and energy are interchangeable. If you burn something, you are converting that matter into different forms of energy. And this was one of Einstein's great breakthroughs, that matter and energy are related, and they are related through this equation. And so what you really need to take away from this is that matter and energy are related. You don't need to remember this whole complicated equation because you already remember E equals mc squared. But there are other types of energy. There are many different types that we will study this semester. And these include kinetic and potential energy, as well as mass energy, gravitational energy, and nuclear energy. We've talked about kinetic and mass energy when we were talking about Einstein's equation above. We'll learn more later about what potential energy is. You may have heard that in a physics course before. And gravitational and nuclear energy may be new terms to you, but they are very relevant in astronomy because stars exist because of gravitational and nuclear energy. And so we'll learn about that in this course as well. And each one of these types of energy describes how matter is currently moving or could move through space depending on what it's currently experiencing, what its physical characteristics are. So, space and time. Einstein, another one of his great breakthroughs was that they are linked. So, space is what we refer to as where matter and energy exist. It's the stage on which the actors matter and energy can play out their little dance. And so wherever matter and energy can be located, this is where you can think of as space is. Space is a very abstract concept if you think about it more deeply, because we all know like 12 inches to a foot or 1,000 meters in a kilometer. But when you think about what is space actually, you can't really define space without thinking about the stuff that's in it. Your ruler has that length because of the amount of matter that takes up that space that is the ruler. The foot exists because there is a foot of mass right there. You can't really separate space and matter. But matter also has energy and it moves through space. And so if you want to describe how something is moving, you need another component, another dimension, one that we call time. And this is how matter changes. This is one way we can think of how matter changes its location in space, is that it's also changing, it's moving through time as well. So I'm going to give an example that is a little more concrete. You have some stuff at point A and it has some energy. And that energy is going to allow it to move to point B. And so, because things in our universe don't travel instantaneously, it had to take some time to go from point A to point B, because that matter was not previously at point B. It had to move through space to get there, and it had to use energy to get there. So this brings us to our place in space. So astronomy is the study of the universe, but what does that mean for us here on Earth? Where is Earth? How significant is Earth? Are we super special? Well, after thousands of years of studying and attempting to find our place in the universe, astronomers have found that Earth is the third of a rocky planet system from the sun. It is the third rocky planet from the sun, which is itself a rather average star. It is a yellow dwarf star that has a relatively small solar system with only 8 planets. And when we look at other stars, we find that in a galaxy like our own, there are about 100 to 400 billion other stars in a galaxy like our Milky Way, which is a spiral barred type galaxy. And when we look for all of the other galaxies, we find that there are about 100 to 200 billion other galaxies in the universe. Each one of those galaxies has their own stars, their own billions of stars, and each one of those stars likely have planets. And so we find that we are in a vast ocean of stars and galaxies and planets. And this may make us seem insignificant, but I actually think it makes us very special because we are able to observe and experience all of the wonders that are contained within our universe. And so this semester, we will get to experience and explore these wonders together. Space is huge. It is vast. It is enormous. It is gigantic. And to really get a scale for how vast our universe is, we need to understand what units we are using to measure things in our universe. So, the everyday units that we use to measure things around us, like feet or inches for distance, or Fahrenheit for temperature, these make sense for our everyday uses, but they don't have as much meaning when we have such large scales that we encounter in astronomy. So, in astronomy, we use the metric international system of units, more commonly referred to as SI units. So, in astronomy, the base unit for distance is the meter, but we often use other units that are based on the meter for distance when we are talking about things that are lots of meters. So, an astronomical unit and a light year are two other distances that we commonly hear in astronomy, and they are lots of meters. We'll see on the next slide how many meters a astronomical unit has and a light year has, but it just makes more sense to use a single unit when you have that many meters. And then for temperature, we'll be using Kelvin instead of Fahrenheit. So for distance, for things that are nearby, it makes more sense to use these smaller base units of distance, such as the meter. But when we are looking at, for the example, the Earth's orbit around the sun, it doesn't orbit in a perfect circle, it orbits in a slight elliptical shape. And so at the furthest point from the sun in its orbit, known as the aphelion, it is 152,000, sorry, 152,100,000 kilometers from the sun. That's quite a mouthful. And when it's on its other side, at the perihelion or the closest approach to the sun, it's 147,300,000 kilometers. So, when by taking an average of that, astronomers came up with the unit, the AU, which is much more convenient to describe the distance between the Earth and the Sun. It's the average distance the Sun is from the Earth during its orbit. And it's just much more convenient than saying that the Earth is 5.79 trillion inches, for instance, from the Sun. That is a little cumbersome, and I can't picture 5.79 trillion anything in my head, but I can picture 1 AU. I can picture this diagram and think, that distance is one astronomical unit, rather than trying to remember a crazy number. We've been talking about the extremely large scale of distances, like between the Earth and the Sun, or between other stars, but astronomy is also concerned with very small distances and very small scales. Most of the atoms in the universe are hydrogen and helium because they are the simplest elements on the periodic table and are the easiest to produce. They make up almost the entirety of normal matter in the known universe at 99.9%. And there is almost 10 times as much hydrogen as there is helium. So if we're going to talk about the universe, we have to be able to talk about the small scale as well. Atoms are most usefully measured on atomic scales. And the hydrogen atom is so small that its radius is approximately that meters in SI units. But back to the extremely large scale, and this is where meters begin to fail, and even the astronomical unit is not enough to describe the scales that we're dealing with. So, for example, the Milky Way is 1 sextillion kilometers across, which is almost 7 billion times the distance between the Earth and the Sun. So, 7 billion AU across the Milky Way. We're going to need a better unit for objects that are this large and not nearby. So we're going to describe things in terms of light years. That is the distance it takes light to travel in 1 year. So light travels at a constant speed of about 300 million meters per second. That's the speed of light. So in 1 light year, light travels 9,460,000,000,000 kilometers. That's really far. And yet the Milky Way is 110,000 light years across. And so we think of that as a large distance. But the distance between the Earth and the Sun in light years is much smaller. And then the radius of the hydrogen atoms in light years is so small that it's almost meaningless. In fact, the wavelength of light all the way up to the gamma rays, only the most extreme gamma rays have wavelengths that are smaller than the size of atoms. So atoms are smaller than light itself on average when we think about light as a wave. The units of time also have a great scale and varying degree of magnitude in astronomy. We are concerned with events that happen in the blink of an eye. Supernova can happen, such as type 2 supernova, which is the death of an extremely massive star, such as a star that's 15 to 90 times the mass of our own sun. It will collapse down to about 20 kilometers in less than a quarter of a second. In the time it takes, in less than the time it takes to blink, that star will have gone from larger than our solar system to down to the size of a small city. That's an incredibly short time. And yet, that star's lifespan could have been in the millions of years. And we'll find that less massive stars can live even longer, into the billions of years. And so now we're talking about the billions of years. And so that's bringing on this new scale, the cosmic time scale, when we're thinking about things on the largest time scales possible. So our universe, based on calculations from Hubble's law and studying quasars, which are galaxies that are very bright but very far away, astronomers have concluded that our universe is 13.77 billion years old. That's pretty large number if we think about that in terms of how long it would take to do anything. I mean, our lifespan is about 75, 80 years, and we're talking about billions of years. Cosmic time and the time scales that we're thinking about when we're talking about the creation of the universe and how it evolved from the very beginning to now require us to think on enormous time scales. So now that we've talked about some of the units and the scales at which astronomy works, and we've heard about some of the things that astronomy has told us, we need to now understand how it is done and a little bit about the history behind it and how the scientific method partially emerged from astronomical observations. So the earliest astronomical observers, the earliest astronomers, were very limited in their technology. They could really only use their eyes and pencils and papyrus to draw the constellations that they could see in the night sky. And so when they were looking out at the night sky, these observers imagined that these constellations were fixed points on what they thought of as a sphere around the Earth that was known as the celestial sphere. And the Earth was in the center of this sphere, and it rotated around the poles, which were connected to the north and south celestial pole, with Polaris, the North Star, directly above. And so the heavens would rotate annually around the Earth. And so, to explain these constellations, many of these observers developed complex mythologies to describe the origins of these constellations in the sky. Many of the constellations we know of currently, or many of the constellations that we know in the modern day, are based in Greek origins, but cultures around the world had their own constellations and their own stories about the stars. And so I encourage you, when you look up constellations, to look up what other peoples thought of these constellations, what native astronomers called their constellations, and the stories behind them. Ancient astronomers were very interested in the night sky and the constellations. And by paying a lot of attention to them, they noticed that some of these constellations were very predictable and that the sun's path through the sky, which is known as the ecliptic, one of these 13 constellations would appear in the celestial sphere along a band centered along this ecliptic seasonally. So these constellations located at a certain central part of the sphere, the celestial sphere, at sunrise and sunset, are called the astronomical zodiac. And so these are the zodiac constellations that we hear associated with this pseudoscience of astrology. Astrology is this idea that when you are born, the stars that were in the sky at that time somehow determine your fate. But we know through scientific study and methods that these are just stars out there. They don't have any connection to us. In fact, the light that it took for them to reach us has taken hundreds of thousands to sometimes millions of years to reach us. So they're not connected to us. They just are shapes in the sky. And so each one of these zodiac constellations had associated dates. And so they were very useful for keeping time in terms of the seasons and the months in the year. And so this brings us to a discussion of the scientific method, because now we've discussed a pseudoscience of astrology. So the early philosophers in 300 BC employed Aristotle's scientific method to improve their understanding of the universe. So it's really important to know what is science. And the foundation of science is the scientific method. And this is how we can determine what is a science and what is not a science, what we would call a pseudoscience. So the scientific method is that you observe something, you hypothesize and theorize what caused your observations, and then you test out your hypotheses and theories, and then you come to a conclusion. Did your hypotheses and theories match your test? And then you often repeat that so that you can make sure that it wasn't an error. So observation is our first step. This is when you see something in the natural world. Hypothesize and theorize is when we develop a framework of ideas which can explain what we observe. And then to test something, to test and conclude, this is the one of the most important steps, because this is how we derive theories and laws, because they must be testable. Testable principles govern the behaviors that we see. So if you think that you have a new theory of motion, you need to be able to show that something can move from point A to point B in how you describe that motion. Otherwise, Newton's laws of motion still govern what we are seeing. And this is how we can test new theories and ideas, through the scientific method. And then lastly, we have to repeat our observations, hypotheses, and testings and conclusions, because it is very possible that we made an error along the way, and we need to be able to repeat it. The repeatability by other people is the key to having a theory be proved. Another group needs to be able to conduct your experiment and get the same results. So you might be now seeing that science isn't a very linear process. There's no one question or one answer that we're looking for. Instead, science is progressively looking at different things to spark new big questions and attempt to answer what mechanisms are involved in that question. So, an example, one of the most famous, is Newton with his apple that fell and how he thought of the theory of gravity. So, the scientific process uses the scientific method. We have our verifiable scientific fact: an apple fell from the tree. Our scientific theory: a force that we'll call gravity exists, which makes things fall, in this case, the apple. Now we have our law that we need to be able to test. The apple fell with a changing speed, attracted towards the earth. And we have our new scientific theory, and this is always amendable. Theories can change. And our theory is that the earth's gravity is a field due to the earth's mass bending space. But no one asked initially, what is gravity, or even tried to answer that question. They were just trying to describe how the apple fell and why it fell the way it did. And this gave them the ideas of these laws and these ideas of gravitational fields. Science isn't always smooth, but it is always advancing, and sometimes it makes big leaps, such as when Newton thought of gravity, or when Einstein refined gravitational theory into the theory of relativity. Observations are the basis of how scientific inquiries begin. We have to see something before we can come up with ideas to test. And we've been talking about astronomy and how things in astronomy are extremely far away. But how do we know that they're truly far away? So one of the first methods used by early astronomers was triangulation. This was thanks to Pythagoras and his right triangle geometry. So if we've got something very far away that we're looking at and we want to know the distance to it, if we have an observer go from point A to point B and we know that distance, we'll call that distance the baseline. And then we can measure the angle that you have to change to observe the object far away. We can use geometry to find that unknown distance. This is known as triangulation, and it is the basis of what we call the cosmic distance ladder. That is the family of distance measuring techniques that are used to chart the distance to the universe. or the distances to things in the universe. There are a lot of different techniques that are good for different distances. So some are better for closer things and then are able to then be connected to other methods that are better for things further away. And so each one of these techniques is a different rung in the cosmic distance ladder. Now let's take this concept of triangulation and measuring distance with it and apply it to astronomy. So when we're measuring distances using triangulation in astronomy, we need to look at the parallax. That is the apparent motion of the foreground object that we're looking at relative to its more distant background. So the larger the baseline that we are using, the smaller the angle of observation becomes, and so the greater the parallax. When we have very large baselines and large parallax, sorry, these very large baselines and large parallax are necessary for our observations because if the angle is too large, a triangulation method cannot be used. You can try out measuring parallax yourself with a little experiment. If you open and close your eyes while holding out a pencil in front of them, you can see the parallax change as you move the pencil further away and closer to you. You can see the relative distance changing. Triangulation can be used for more than just measuring distances, though. In the mid 300s BC, Aristotle saw the curved shadow of the Earth on the moon during a lunar eclipse and postulated that the Earth was round. But it wasn't until the 200s BC that using triangulation, the Greek mathematician Eratosthenes was able to test this "is the Earth round" hypothesis. So Eratosthenes noticed that on the first day of summer at noon in Syene, now Aswan, Egypt, vertical objects cast no shadow, and that the sun's rays were able to shine directly down deep, narrow wells. These rays were directly overhead of these wells, and the rays were parallel with the walls of the well, so they could go straight down. However, at noon on the same day in a nearby city of Alexandria, which was 500 stadia, that was the distance, the unit of distance that they used, their baseline, objects cast a 7.2-degree shadow. This was their parallax. And so using the angular relationship, they were able to conclude that the Earth's circumference was about 250,000 stadia, or 40,000 kilometers, which is in 1% of the known number today. And that's really incredible that mathematicians and philosophers so long ago were able to calculate the Earth's circumference so accurately using simple geometric principles. And these same principles can be used in astronomy as well to measure things in our nearby universe, such as nearby stars. And so this concludes the first lecture. There will be lecture part 2 as well.